Thanks very much. Okay. Good morning, and welcome to this webinar, our webinar on the overview of the four-step transport demand model. And some housekeeping. The duration of this webinar is about 1 hour, and the presentation will be about 30 to 40 minutes, and some time will be allocated for questions. At the end of the webinar, all participants will be emailed a PDF copy of the presentation. And you can ask questions at any time by typing them in the question box, and I will answer them in the question time at the end of the presentation. Okay, that's so. What do we aim to achieve with this webinar? What I've set out is that we'd like to give you an overview of this transport demand model. In other words, we'd like to tell you exactly what is a transport model, or the four-step transport demand model, and also some idea in terms of what it can and what it cannot do. So hopefully that will at least give you an idea of when you receive, for example, if you're a road agency and you receive a consultant's report on transport demand model, you at least have some appreciation of what it can and cannot do. So firstly, the purpose of a transport demand model is really to analyze strategies. And you can see here in this slide that the transport demand model actually can analyze two types of strategies. One is the urban development strategy, wherein you say, for example, provide relocation of population or employment in various parts of the city, and you like to find out whether these strategies work or not. The other one is transport strategies, and the same way we would like to analyze whether investments in transport, say building a new motorway or building a new railway, will benefit the society or not, or whether they're value for money. So the transport demand model is sort of like our crystal ball, where we can look into different scenarios or different configurations of the city and check whether they make sense or not. So then from the transport demand model, we can derive various performance indicators, and these performance indicators will tell us whether these strategies make sense or not, or whether there is value for money. An example is this particular graph, which was used in the planning of the port of Hai Phong and Cai Lan. The port of Hai Phong and Cai Lan are located in northern Vietnam, where Hanoi is, and these are the primary ports in that region, and the operation of this port is critical for the sustained development of the region, particularly that the northern region of Vietnam is moving towards export-oriented industries. So therefore, it's really critical to know whether the ports of Hai Phong and Cai Lan are going to be up to the task. And this graph shows you the projected traffic or cargo for all cargo and for containerized cargo. And you can see that there's a bit of a spread. There's a high-end estimate, a low-end estimate, and a likely estimate. For containerized cargo, this is the same with a bigger spread. The reason being, there's a lot of uncertainties involved in the forecast of containerized cargo. So therefore, there's a spread so that we can appreciate with whether some of the risks involved in investment. Now, this is then useful for us to have a discussion on when do we expand the ports of Hai Phong and Cai Lan. Say, for example, the current capacity, say, is 20 million metric tons per year, with a capacity of, say, for example, 1.5 million TEUs per year at the moment. So therefore, when this graph would then tell us when we should have the new capacity or even a new port built such that there's no disruption to the economy. So this gives us a way to prioritize investments and also determine the scale of investments and the nature of investments. So in this particular case, we need to move away from bulk shipping or palletized shipping services towards containerized shipping services. So this gives you a snapshot of how useful transport demand forecast model is. But then again, we have to remember that it is not, we always forecast with uncertainty. So therefore, we need to remember that while the transport demand models can give a number, there's actually a spread, and an appreciation of that spread will give decision makers a better source of information so that they can take account into demand risks when making vital decisions, such as building a particular port, which would cost billions of dollars. So essentially, what is a transport model? A transport model is nothing more than equations representing the choice made by individuals when they travel. And as in any equation, there's two components or two attributes of the transport demand model. First one is the form. Say, for example, a linear form. Say y is equal to alpha plus beta times x. That's a linear form. Say y is the number of trips, and x is, say, for example, personal income or household income. So the higher the income, the higher the number of trips being made. So that's an assumption that we have to make based on the behavior of a household. And the other component is parameters, alpha and beta. These are parameters that need to be calibrated from existing data, and the discussion to determine alpha and beta are largely technical, which I'm not going to go in this presentation. But what is important here is that each model is really handcrafted for a specific purpose. Say, for example, a particular model y equals to alpha plus beta times income is really designed to analyze the impact of income to trip making and the impact of that to the infrastructure ultimately. If we did not consider, say, for example, age or employment or car availability, now there are hundreds of variables that can be used to explain trip making behavior, but it's really impractical for us to consider everything. So therefore, while a generalized model which can consider all sorts of variables such as fuel price, taxation, etc., it is really not practical. So therefore, we are limited to what we can do, and we have to be aware that the models are handcrafted for a specific purpose. And then when that model is utilized for a different purpose, then the accuracy of that model begins to degrade. Now, there are actually a range or a number of modeling techniques that we can use. It can be grouped into two types: simulation techniques and analytical techniques. Simulation techniques use time steps. So at time t minus 1, the state of the network is that, and then at time t, it moves to a different state, similar to a micro simulation model, as you can see here on the right. Analytical models are more closed-form equations, and the four-step transport demand model falls in that category here on the far left. Sometimes we refer to them as macro models. The software used can be, there are various types of software that can be used, like EMI, Cube, or Visum, or even some proprietary software of ARB, such as ARB Traffic. But inside them, they all have the same mathematical construct. So it's more like akin to a different car model with the same internal combustion engine. So the software really doesn't matter. What is important is the equations inside the software. So in this presentation, we're going to focus on this part of the modeling type of modeling technique, But one thing to remember is that since there are various types, each type has a specific purpose and more useful than other types for a specific question to be asked. Say, for example, if you're talking about traffic signals, the impact of dynamic systems such as traffic signals which changes over by minute, then the technique to be used should be microsimulation. That cannot be analyzed using macro model techniques. So we really have to be careful in choosing the type of modeling technique to use. But in this case, we're focusing on macro models which are designed for strategic transport planning or land use planning or integrated land use transport planning, investment planning, feasibility studies of large-scale infrastructure, and the like. We differentiate trip purpose. The reason being is that each trip purpose has different characteristics. So to work trips behave differently from shopping and recreation trips. We are more, we tend to travel longer distance for work trips and less for shopping and recreation. So therefore, it then becomes necessary for us to differentiate between trip purpose. And there are basically three types or three ways we can model this trip purpose in the sense of trip chaining. So the most accurate one is what we call as activity-based models. Activity-based models trace the activity of the traveler or the agent from home to work to lunch to work to home and shop and so on. Each activity consumes time, and the traveling also consumes time, and there's benefits involved in each activity. So therefore, the activity-based models can really incorporate and combine all those decisions for each traveler, and therefore had a very realistic modeling of the decisions being made. This comes as close to reality as we can get. A compromise for that is called a tour-based model. In the case of tour-based models, there's a finite set of tours. One tour is a home, work, lunch, work, home. That's one tour. Another tour is home, shop, home. And based on this finite set of tours, each traveler will then choose the particular tour based on several constraints. So the activity-based and tour-based models are quite realistic, but the four-step model is the more conventional one, and it's sometimes called trip-based modeling. In this particular case, this more realistic trip is divided into 6 different trips: home, work, lunch, work, and so on. And each type of trip is one trip purpose and is modeled differently, and there is not much interaction, or there's some interaction, but not in a more explicit way as activity-based model does it. So there's a bit of limitation in the four-step model in terms of modeling trip chaining, but nonetheless, when again it's a horses for courses issue, where when we are more concerned of, say, trip chaining, then we have to use activity-based models. But if we are more concerned with regards to, say, determination of the ridership of a particular railway line, then the trip-based four-step model is the best approach. Now, what is the four-step model? The four-step model structures the decision of a traveler into 4 parts. Firstly, do we travel or not? That's generation attraction. And the next level of decision is, okay, if we travel, where do we go? So that each of the trips will then be assigned to a particular destination. The next question then, okay, if I travel for a particular destination, what mode do I use? Mode means whether I use public transport, car, walking, cycling, ship, ferry, whatever mode of walking, cycling. So that's the third step, which is mode choice. So we then disaggregate the trips or classify them in terms of the type of mode that's going to be used. Finally, once we decide to go by a particular mode, say by car, we then determine the route to take. So whether you take a freeway route or a town bypass route or a circumferential route, this is determined at the last step. This is done the same for transit. So if you have a railway network, the traveler will then choose the route within the railway network to go to the destination, either as quick as possible or as cheaply as possible or as with least amount of transfer as possible. And through the combination of these four decisions, we can then model the trips being made in any city. Okay, let's look at this one by one. Trip generation attraction. Trip generation attraction modeling uses the various attributes of a trip maker or place to estimate the number of trips. This in front of you is the ITE trip generation report. This is the 8th edition. I believe there's a newer version, but it illustrates the relationship between the number of trips that a particular shopping mall or a shopping center will attract given the gross leasable area in terms of square feet. This is US, so it's in square feet. You can see here that there's actually a lot of variation. Each dot is one specific shopping center, and there's a lot of variation. Although there's a clear trend, there's a lot of variation in data. So we take into consideration different types of shopping center then, whether it's primarily retail, primarily grocery, to be able to improve the accuracy of our estimates. But nonetheless, this technique, this graph shows you very clearly a good estimate of or a clear relationship between attributes of the place, in this case in terms of gross leasable area or square area, and the number of trip ends. So the same thing with any area, say for example population. If the particular area has a higher population, it will generate more trips. If a certain area has a university, then it will generate a certain amount of trips as well, and also at the same way attract this a number of trips as well. So that is the role of trip generation and attraction. So once we determine how many trips are being generated and attracted to a particular place, we then move to trip distribution. This is Metro Manila, and what you see here is what we call as desire lines. These, we divide the area into zones or sub-areas, and we can then connect two sub-areas and then determine the number of trips being attracted from a particular origin to a destination. The circles here you see is the proportion of intrazonal trips. So if trips are made within the same zone, that's the proportion here of yellow. And you can see here that the trip distribution is actually based on two important considerations. First one is the attractiveness of the destination. That means, say for example, in the case of Manila, these areas here are CBD areas. So therefore, there's a lot of jobs located in these areas. The more jobs located, therefore, the more attractive that is to a particular from a particular origin. So therefore, more trips are going to be attracted to that place. But there's another consideration, which is the generalized cost of going to a particular destination. Say, for example, in the right-hand side here, you see somewhere in the suburbs that even though it takes long distance to go to the CBD, more people actually go there because there's less available jobs in the area. But then, even though there's less jobs available in the area, in the close proximity, some people still go there primarily because of convenience. So therefore, there's two important considerations. One is the attractiveness of destination and the generalized cost of going there. So if we take into account those two, we can then formulate a model that will replicate the decision for trip destination choice in this or trip distribution. The next step is mode split. This is the one in front of you is a rather old graph, but it illustrates the point quite well. And this is an empirical graph developed in the 1975 for the Bay Area Transportation Study in US. And you can see here the travel time ratio in the x-axis between rapid transit and time by auto. And then on the y-axis is the percentage of total person trips diverted to the rapid transit. So there, if the ratio decreases, that means the travel time by rapid transit is faster by car. Therefore, more trips are gonna use the rapid transit. Now, while the more modern techniques use the logit model, but this empirical curve shows that there is a competition between services. It's essentially a competition between the rapid transit service and auto. So depending on the attributes of the rapid transit, which can include not just travel time, but also travel cost, convenience, and other modal attributes, this has to be compared against the competing modes such as auto, walking, cycling, and then based on the mode that has the most advantageous attributes, that will get chosen or more likely to be chosen. So then we can then differentiate or disaggregate the trips coming from a particular origin to a destination based on the type of services offered between the 2 points. So this is very useful because then if we have, say, for example, a particular target for mode share, we can then easily design what should be the speed or the travel time by a particular mode, say transit, such that we would be able to attract, say for example, 50% of the trips by transit. So it's not only used for design, for prediction purposes, but it can also use for design, so not just for prediction, but also for design purposes, to design what type of service to be able to meet a particular mode share target for a particular city. All right. The next step then, say for example, we have determined the number of trips by car going from point A to point B. The next decision to make is which route to take. This is a map of Brisbane from Google Maps. And you can see here that for this point, that point, the preferred route is on going through the Pacific Motorway and the inner city bypass route, as opposed to, say, going through this particular route, which includes the Clem 7 and all the way to there. So the decision to make for route choice is the same as your GPS navigational system, which is based on the least amount of travel time. Of course, we have to consider the generalized cost, which includes toll as well. So the least amount of the route that will take you from point A to point B with the least amount of time is through this particular route. So therefore, this particular traveler will take that particular route. Now, but there are a number of travelers also making the same decision. So when everybody uses, so firstly, when everybody decides to use this same route, since there is only a limited capacity for, say, Pacific Motorway, congestion will start, and as a result of congestion, travel time increases on this route. So when travel time increases to a certain level, this alternative route, say the Clem 7 route, even though it has a toll level, will become more attractive, and therefore some of the travelers will then move to that particular route. So there's a balancing effect between supply and demand, such that people will shift from one route to the other until the network is in equilibrium, and it's become what we observe on a daily basis and what we refer to as the routine traffic. That's in the network in a state of equilibrium. So that is useful because then we know, say for example, if we're an investor in CLEM 7, we know how much traffic is going to use CLEM 7, and if we have a particular toll fee, we can then calculate the return of investment on that particular tunnel. Then we can get some valuation and make a judge whether that sort of investment makes sense or not. So that essentially is route choice. Now, we of course have different trip purposes, as earlier mentioned, and there are work trips, shopping trips, and others like going to the school, going to business, etc. Each type of purpose will have its own generation and attraction model, an OD model or trip distribution model, and mode choice or mode split model. And then after this particular step, trips are then combined to a car OD and a transit OD, and then finally the fourth step is done for each OD or origin destination. So car origin destination is loaded into the highway network for route choice, and the transit origin destination is loaded into the transit network for transit assignment. And then that's essentially the end of this of the four-step model. Of course, there is to get a consistent solution for each step. There must be some feedback that between each module, say highway assignment and transit assignment, passes information between two modules. Say for example, in the case of tram, where the tram speed is related to the highway speed, so therefore the information is passed between the two. The same way, because of congestion, after the highway assignment and transit assignment, there's a better estimate of travel time, and then that is then fed back into the earlier stages, say for example in the origin destination, wherein the destination choice is dependent on travel time, and that when that information gets fed back and we calculate again and we do it again. After several iterations, a consistent solution will present itself, and that would then be our answer. Now there are two variations, main variations of the four-step model. The first one is the more simplified one called trip end model. In the trip end model, we essentially skip the mode choice step and combine it with generation and attraction. This is in the case where a particular city, the choice of transport is largely dictated by the availability of car. Say for example, if you have a car, then there's virtually zero chance for you using a public transport. This is in the case of, say, a rural town, or even some town in cities in New Zealand uses this trip end model approach. The more common one is the trip interchange model, where we have the conventional four-step, four levels of decisions: generation, distribution, mode choice, and route choice. Now, study period. When we do the four-step model, we have to define whether we're doing it as an all-day model. All-day model means we are having the demand for 24 hours all in one go, or in some cases 16 hours. Anyway, long periods of time representative of daily traffic. This type of model is typically used by the Department of Planning or Department of Transport, where they're not really concerned about the hourly fluctuations within the day, but they just want to know how many trips per day is going to use a particular railway line. Most of the or all of the road agencies tend to use what we call as a peak hour model. In a peak hour model, we model only 1 hour or 2 hours. In this case, we adjust the 24-hour demand to a peak hour demand. So say for example, the peak hour demand can be 12% of the 24-hour demand. So therefore, you have a more intense congestion levels at that particular hour, And that is useful for road agencies because they're more concerned of the peak hour conditions than, say, for example, a daily, which is more for investment analysis. There are also multi-period models, and they become a little bit more complicated. And in this particular case, we need to consider another decision to be made, which is the departure time choice. In the four-step model, the departure time is not included. So with having a multi-period model, the departure time choice can be added. In that case, the traveler can decide whether they're going to leave early in the morning, say 6 o'clock, to avoid the rush hour, or even leave later, the AM peak, say leave house from 8 a.m. to avoid the peak hour rush. The usefulness of a multi-period or a model with a departure time choice is that we can model more accurately the peak spreading issue. So what is then for example, there's a particular research done on Tokyo where the policy of staggered work hours was analyzed to check the impact of that particular policy on train congestion. And it turned out to be that, yes, it has a good impact. Of course, then we have to design the staggered working hours accordingly such that we can derive the best outcome, both from a transport perspective and from a business perspective. Okay. Now, this slide in front of you is called the zoning system. And this is the foundation of the four-step model. Say, in this case, it's Perth. And on the left side is the ROM model, or the regional operational model. And the right side is the strategic transport evaluation model. One's operated by the Department of Transport or Department of Planning. The left side is operated by the Main Roads WA. It's the same city, but the resolution of zones are different. Here you have 472 zones, and on the left side is 1,146 zones. The reason being is that the road agencies are more concerned about the smaller level, higher resolution in geographic resolution of analysis because of the analysis more with regards to intersections, mid-blocks. So they need higher resolution for their analysis. Whereas in the case of Department of Planning, they're more concerned of strategic investments such as a particular railway, particular motorway, and minute details within the zone is not really important for them. So therefore, again, horses for courses, depending on the purpose of the model, we have different types of zoning system. But another thing is here is that the zoning system is the foundation of the four-step model. So therefore, all the generation and attraction is calculated on a zone level. So in a particular zone, for example, this one, it has a number of population, number of employment within the same zone, number of enrollment or school seats, retail space, and others. And then that will then be the basis of calculation of number of trips being generated and attracted from a particular zone. And that will then be connected to another zone for origin destination. Okay. Once the origin destination is determined, then we go to the next level, which is the link node network. This is the link node network for Metro Manila. And this link node network is a link node representation of the transport system. So you have highway networks there, you have railway networks, bus networks, and so on. And the links and nodes determine the connectivity between zones. So if you go from one particular area to another area, then this is the connectivity of the links and nodes will tell you the distance between those 2 points, or the running distance between 2 points. And then this will then, each link and node has a particular capacity. So if demand increases or comes close to capacity, the travel time on that particular link increases as well as a result of congestion. So this link node representation is then used as the basis for route choice. and also for mode choice. Okay. Much of the data for developing a four-step model comes from the census. Population, enrollment are all coming from some sort of census data coming from various government agencies. But there's a special survey that's being done specifically to develop the four-step model, and that is called the Household Interview Survey. In the case of Melbourne, it's called the Victorian Integrated Survey for Travel and Activity. This is a special type of survey where we do roundabout somewhere between 1% to 3% of households in the particular study area or city, and we come to each house, knock on their door, and interview everybody in that particular house where their travel behavior on a particular day. So, say for example, if we ask persons in that household, what was the first trip? What was the stop one? Where was it? Who traveled in that particular with that traveler in that particular trip? Why did you go to stop one? How did you get to stop one in terms of modes? And what kind of vehicle did you use? Or what time did you arrive? So all this information is collected and compiled into a transport database and used for development of the four-step model. Okay, now we go to some of the limitations of the four-step model. There's probably a few of them, a number of them, but I'm going to list ones that come to mind, probably the major ones. The first one is there's no feedback with transportation plans. That means that the population or the employment for a particular zone does not change with transport plans. Say, for example, you build a particular motorway, and since you build a particular motorway, that area along the corridor becomes attractive for development, say, for example, residential development. So therefore, by building that motorway, more people are going to live in that area. That feedback does not exist in the four-step model. You need to go to a more complicated model, which is an integrated land use and transport model, to be able to do that. So that's one limitation. But that doesn't really mean that there's no feedback. It's just that the feedback is implicit rather than explicit. So when we do the transport plans, we do allow for certain scenarios where population in that particular corridor will increase. So that is done through expert judgment rather than through an explicit modeling approach, which is beyond the capacity of a four-step model. The performance for predicting freight is still poor. Reason being is that freight decisions are somewhat different than private transport decisions. So in freight transport, logistics considerations come into play, and the decisions for logistics is related for manufacturing strategies, marketing strategies that are beyond the four-step model. Although we try to provide some analogy with freight transport, it's just not the same or not as accurate as in the case of private transport. Another reason is that freight is highly disaggregated or differentiated. That means bulk transport, say coal transport, behaves very differently from TV transport, or milk transport is different from cattle transport. So for the moment, the performance for predicting freight is still rather poor. Intrazonal trips are not satisfactorily modeled, with implications to walking and cycling. This is an offshoot of the zoning system. Say if you have a very rough zoning system, then the trips within that zone could not be modeled properly. You can, of course, have smaller zones, but then still you can never go to the same level of 100, a certain level of resolution where can you really model walking, say for example. Walking trips tend to be short distance and it's just not possible. So there are some limitations in that case. As illustrated earlier, the trip chaining phenomena could not be modeled properly as opposed to, say, an activity-based model. Okay. Okay, next few slides is some examples. Here is an example again of northern region of Vietnam where you have the highway number 5 connecting to National Highway to Hanoi and Hai Phong. And these dotted lines means that the do nothing network or do not do anything for up to 2020, the level of congestion would be very, very high and travel time would be very, very high to the detriment of the competitiveness of the region, especially since Hanoi is where the region, where the industries are located, and Hai Phong is where the port is. So by having that congested link between the two would create a lot of disadvantages to the region. So the solution, therefore, then is to build this big super expressway in the middle of National Highway 5 and National 18, and the transport model will then predict or forecast that the congestion levels at National Highway 5 and National 18 will go down, and this will still be operating well. So therefore, the problem is solved. Now, this is a solution. This is a type of approach called predict and provide, and this is not good practice because in this particular case, this solution or this proposal was presented to higher levels of government decisions, and it was rejected, and in favor of a southerly route between Hanoi and Hai Phong. While that route will not address the congestion issue more directly or more effectively as this particular central route, it does open up the land in this area for development. So therefore, the solution, the approved solution then is actually to build an expressway in this area, and this was then downgraded from, say, for example, from a 6-lane expressway to a 4-lane expressway. So that illustrates to you that the transport models are not to provide you with a solution, but rather it's a tool for you to test your solutions. And we should not be guided blindly by what the model says, but we have to take into considerations various other developmental issues such as regional development when we design solutions. Okay, a reality check. This graph shows you the documented accuracy of the 4-step model. In the case of road projects, it's about plus or minus 30%. While it doesn't seem so accurate, it's not so bad because there's a bit of a spread here, and there's no bias or very limited bias in the sense that it is not the average is not overestimate or not underestimate, but there's a spread across 0. So, but in the case of rail, this is a bit worrying because in the case of rail, there's a bias towards optimism, and that is the experience. And the reasons can be technical, but the ones that I highlight here is that one of the reasons for inaccuracies in forecast is deliberately slanted forecast. This is based on a review in 2006, and I can say that based on experience, this is really true. So therefore, we need to be careful with reading and consuming various transport models results. So we need to be aware who did the forecast, and is there any conflict of interest of providing such a very rosy picture of the future. And it is since we're going to build billions of dollars, invest billions of dollars in these particular projects, it's really advisable to seek independent audit of these transport demand model forecasts. And roads, though, is not immune to this, in particular tolled roads. So you can see here various projects in Australia, and you can see here the forecast daily traffic in the first year and what was actual. And you can see there's a lot of discrepancy. So again, it's really due diligence and checking and getting independent audits to get a more reliable forecast when we're dealing with this kind of issue. So this ends this webinar. Thank you for presentation. ARB does conduct, we did not go into too much details in the transport demand models itself. We do have a seminar which we conduct where we have details. It's a 2-day seminar, and if you're interested in that, watch our knowledge transfer page for further information for that. For now, I hope that you find this presentation informative, and I'm happy to take questions. Okay, so far I have not received any question. Okay, so okay, how many transport demands are there in practice? From how many transport demand models are there in practice? A question from Bishes, Mr. Bishes from Bishes Pokrel. Sorry if I mispronounce your name. Let me try to understand that question a little bit more clearly. Transport demand models are there in practice. Well, if you're talking about the 4-step model, is only one really. The difference can be in terms of the software used, and each model is really handcrafted for a specific purpose and for a specific location. So each city have their own transport model in that sense. So there would be as many transport demand models as there are cities in the world. But in essence, if you boil it down to their fundamentals, there's really only one at the moment. There are certain cities, say for example in the case of Australia, most cities use the conventional 4-step model, but say for example Sydney is using tour-based approach. So, and I'm not updated in my information, maybe that's 3 years ago, but certainly some cities are considering moving towards, or at least developing as part of their arsenal, both the 4-step demand model and either an activity-based model or a tour-based model. Slide 16 shows your work trips are car. Slide 16, going there. Okay. In question from Malav Shah, in your slide number 16 graph, slide 16 graph shows work OD trips are by car only. Oh yes, that's just a typo. There should be a arrow towards transit OD, of course. Sorry for that. So in other words, there should be an arrow, and the work trips are included both in transit OD. An interesting offshoot of I can think of that question is that how about park and ride? So park and ride is a combination trip where you both you have a car component and a transit component. How is that modeled is by park and ride becomes one of the trip purpose, and the car component that's from home to the railway station is included as part of the car OD, and from the transit from the railway station to the destination becomes a transit OD. So that is the how trips are assigned for car OD and transit OD in the case of park and ride. Okay. Any more questions? Okay. Which sources is the best for trip generation? ITE or tricks or local? Unfortunately, I don't know what, I'm not familiar with tricks, but certainly, say for example, in the case of the ITE, all right. In the case of Australia, the commonly used or the more authoritatively used trip generation table is the RTA one, or what is now called the Roads and Maritime Services. They have a trip generation or trip rate guideline, and that guideline is commonly used in Australia. Now, I compared that guideline with the ITE one, and the Australian one, or the RMS guideline, is on the high end of the ITE guideline. So therefore, in the case of Australia, the number of trips being generated per gross leasable area is on the high end compared to the case of United States, or in the case of the ITE. So therefore, that gives you that while these trip tables are very convenient to use, there's a lot of variation between cities. So the local one is definitely the best one, because that incorporates the nuances or the specifics or particular conditions of any given area. The last choice would be something from international. Okay. In the last slide, from Felix Liu, in the last slide, can you go there? Probably this one. In the last slide, it shows all projects have discrepancy on the design and the reality. Is there anything you can do to feedback to the future design? Thank you. Appreciate providing a copy of the comparison between RTA and RTA. Sure. Shows all projects discrepancy. Is there anything we can do to feedback to future design? Certainly, yes. For example, we are working to, I could not provide much details, but we are working to assist private investors looking into toll road projects for as a long-term investment and updating their forecast. Once the toll roads have been operated and opened, information or traffic data will flow in, and we can actually track, say after 6 months of operation, an estimate of what the initial traffic volume using that particular toll road would be. So therefore, that information is very, very useful to update the transport models. So that can be done and should be done. So that essentially is it. We use the after 1 year of operation, when we have collected the actual traffic volume, we can then recalibrate our models. Is there an Australian standards to determine trip generation? Each state has their own standard, but typically, for example, South Australia have their own, and I'm not so sure with other states, but definitely the RTA standard is the one that is commonly used in Australia. Sorry, that was a question from Hiran Wijiratne. Okay. Any more questions? All right, looks like there's none. Okay, none. So again, thank you very much. Thank you very much for attending this webinar, and I do hope you keep on keeping track of our webinar series here at ARB, and appreciate it. Cheers.